Good evening, ladies and gentlemen. In tonight's problem, we are going to assume the flow around the long cylinder in the figure shown below is non-viscous and incompressible. Two pressures, P1 and P2, are measured on the surface of the cylinder, as illustrated. It is proposed that the free stream velocity, u, can be related to the pressure difference, which is the difference between P1 and P2, by the equation shown, where rho is the fluid density. Our task is to determine the value of the constant c and neglect body forces in doing so. So we have a diagram here where we have P1, which is a stagnation point, and P2, which is 60 degrees above that along the cylinder. And this cylinder interrupts a free stream flow of velocity u, and we need to find out what this value c is for the velocity. So we're going to start this by using the Bernoulli equation. We're going to do this at point 1, and we're going to say P1 plus 1/2 rho v1 squared plus rho gh1 is equal to some constant. And here h1 is 0, v1 is 0 because it's a stagnation point, and we'll do the same thing at point 2, where we have p2 plus 1/2 rho v2 squared plus rho gh2 is again equal to some constant. Here we're going to neglect the height component in the Bernoulli equation. It's not tall, it's not that significant, and so we will have P2 plus the velocity component equal to some constant. We can actually, because these are along a streamline, we can equate these, and so we'll say P1 is equal to P2 plus 1/2 rho V2 squared. So right now the question is, what is V2? Now we're going to take a little zoom in here on point 2 where P2 is occurring. And, we're just zooming in on the circle here. Where we have this velocity is actually tangential. So this V2 is actually tangential to the surface of the circle, and that is our velocity. We need to find a way to find the tangential velocity for flow interrupted by a long cylinder. Now we actually have an equation for this. We can go and find, well, we'll put this in a different color. We'll put this in red. We need tangential velocity for flow that is ideal, inviscid, and incompressible. Now, lucky for us, there is an equation for this verbatim, which dictates v theta, which is actually going to be our v2. So v2 is going to be equal to v theta. And here v theta is given by the expression negative u sine theta times the quantity 1 plus big R squared over little r squared, where our little r is equal to big R because we are on the external surface of the circle. So we're at the maximum radius, which is big R. And this turns out to be negative 2u sine theta for v theta. And we can go one step further. We can put 60 degrees in here. And we'll do that and evaluate it. So we'll have v theta is equal to negative 2u sine 60 degrees. And we will evaluate that, and we'll have v theta is equal to negative 2u rad 3 over 2. And that's our velocity. So we'll go on to the next page now, and we will find the pressure differential. So if we remember, we have P1 is equal to P2 plus 1/2 rho V2 squared, and we have the V theta expression. So what we can do is we can do P1 minus P2 is equal to 1/2 rho V theta squared, because remember V2 is equal to V theta. And we'll go again one step further. We'll plug in V theta. We have 1/2 rho negative 2u rad 3 over 2 quantity squared. And this is actually delta P, as we saw in the original problem statement. So we have delta p is equal to this, and delta p, again, will simplify down, where it will be 3 over 2 rho u squared. So now we can isolate for u, and then we'll be able to find c. So what we have is, we're actually kind of come crashing in on this. U squared is equal to delta p over rho times 2/3. And so if you see what's about to happen, we have u is equal to the square root of 2/3 times the square root of delta p over rho, which is the exact equation we started with. But now we have c defined, which is this constant out front. And so because this is c, c is equal to rad 2/3, which is our explicit answer. And so we'll box that and call it a day. Congratulations, we have found the constant.